Okay, here we go. Lesson 12. So far, we've covered speed, velocity, acceleration, the equations, graphing speed and acceleration, Newton's three laws of motion, trolley dash, the required practical investigating second law of motion, calculating forces from vectors, weight, mass and gravity equation, work done equation, Hooke's law, force extension equations, free fall and terminal velocity, and now we're on to stopping distance. And for this one, you are going to need to have a quick look back at the acceleration equations, as that will help you. So without further ado, let's have a look. Right. Scary thought, some of you'll be driving in the next 18 months or so. You'll turn 17 and hopefully you'll get yourself a car. So this one's really important for cars really, and it's called Stopping Distance is our title. Distance. There's two parts to this. I'll do the easy bit first, the hard bit second. So really simply, you're in your car, you've passed your test, you're feeling pretty fly at this point, and you're bombing along. And you look, and we have to guess the animal. Usually it takes a few guesses for this one. And of course it's a badger. It's obvious it's a badger. I think that's what a badger looks like. So you're bombing along. You see a badger in the road, and assuming you're not cruel, some students shout, "I'll speed up." I assume you're going to try and stop. Okay, so you're bombing along. You've left a bit of your car behind. It's that rubbish. You're bombing along, and a couple of things are going to happen. If we were to play this out in slow motion, the first part of it, I'm going to do this in blue. You would travel a distance without changing speed, because during that time you are thinking. This is called the thinking distance. So copy the notes, add it in. What's going on in the thinking distance? Well, your eyes are taking in the information. It's being transferred through the optic nerve to your brain. Your brain's doing some calculations, and then it sends an electrical signal down one of the longest stretches of your body, down to your foot, and hopefully then you'll hit the brake. So that takes time. And for an average human being, the average reaction time is about 0.2 of a second. Whoops. Of a second. Okay, so about a fifth of a second it takes between you seeing something and you reacting. So at this point here, I'm going to put it in red, you press the brake. Okay, now we're over to the physics. So physics kicks in. It's usually further, and this is where the brakes are applied, so this is called the braking distance. So, taken as a whole, we can see that the stopping distance, I'm just going to put stopping, is equal to thinking plus braking. And you can see these written either as the word distance or as the word time. So I'm going to put distance / time. I will probably talk about them both interchangeably. It won't make any difference in this case. Now, you're expected to be able to list what factors would affect the amount of thinking and the amount of braking distance that would occur. So if we were to make a small table like so, and add in thinking here and braking here. I've got my colours mixed up. Let me change my colours. Style blue. There we go. What I'd like you to do, pause the video. I'd like you to write down what things would affect how far you would go in the time it would take to think. So what would make you slower in your brain to react? Also, what things would affect how far your car would skid? So the braking distance. Okay, so pause the video, have a think about it, write them down, and then unpause it and we'll start filling them out. Right, I'm assuming you haven't pressed pause at all and you just wait for the answers, which is frankly what I would do. So thinking distance. Tired. When you're tired, you're not yourself. So tired, drugs. Drugs can have an effect. It doesn't have to be illegal drugs. It can be strong painkillers. And it does actually say on the boxes, do not operate machinery when taking. It could be alcohol, which is one of the most popular ones, drunk driving. It could also be down to your age. I'm not going to put gender because my wife will hit me. Braking. Braking's the physics of it. So braking distance would be the mass of the car. When you're older, and you'll realise when you've got your friends in the car will skid and take longer to stop than when they're not in the car. So the mass of the car. The tyres. TY. Different from tired. Tyres. Are they worn? Are they worn out? The road surface. And that one, there's loads we can write. We can write mud. We can write rain. Ice. Any others you can think of. There is one though, I'm going to put it in green, that straddles both sides, and that's speed. In both cases, the faster you go, the further your thinking distance will be, and the further your braking distance will be. So that's the first page, that's the easy bit done. The second page is with regard to reaction time. So you've done reaction time or you will do it, I'm not sure if you've done it yet, in biology, where if you remember a nice little practical, you've got your hand, you lay it on the table so that it's a fair test, like so, and you get a friend to hold a ruler like that. Let's see if I can get a rectangle. Nope. You get your friend to hold the ruler, and they've got to hold it level with 0. So they get the ruler, and they hold it level with 0 with your hand like so. And then they drop the ruler. So they drop the ruler at a random time. It's got to be random. If you kind of look at your mate and give them the eyebrows, they know you're going to drop it. So you have to totally drop it randomly. This one has got huge amounts of random error. And if you remember, the cure for random error is to repeat multiple times and take the mean. In this case, repeat 10 times because it's quick and easy. 10 times and find the mean. Now, in the biology experiment, you'd get your result, for example, 18 centimetres. Then you would look up a table, and it'd have all the distances, 1, 2, 3, 4, 5, 6, 18. And then down this side, it would have the times, and you would read them off. But this is physics. We have to be able to do it from first principles. So here's what we're going to do. We're going to take this number 18 as our mean, and we're going to find out through physics how to find the exact, the exact time by ourselves. So here's how we do it. This is tricky. Number one, we're going to use an equation, v squared minus u squared equals 2as. Now, why do we want to do that? Well, we want to find how fast it's going. How fast it's going when we catch it. When we catch it. Now, we've got a couple of things going for us here. One of the things is, if we choose a dark green, one is this is 0. Because it's the initial velocity and it's not moving. The other thing we've got going for us is this is gravity. The acceleration is gravity. And this bit here, s, is the displacement. And the good news is that is just the ruler value. So in our case, 18. So let's give it a go. Let's see what it looks like when we put our numbers in. So we get v squared is equal to 2 times gravity, 9.8, times the distance on the ruler in meters. It's got to be in meters, 0.18. So I've got my phone with me. Quick calculation of this one. I really should have got prepared. It's Sunday night and I'm not. Calculator. 2 times 9.8 times 0.18 gives us a velocity squared, v squared, don't get caught up by that, 3.53. So v equals the square root of that answer. So root, let's try that again, clear, root 3.53, which is 1.88 meters per second. So at the point you catch it, say you catch it here, it was going this way at 1.88 meters per second. So that's the first part of this. Using that equation, absolutely crucial that you start there. Pen's not very big, let's try that again. Okay, so that's the starting point. Next, 2. We're going to take this v and we're going to use v minus u over t equals acceleration. And again, we've got some things going for us. This is gravity again. This is 0. This we now have, and this here is what we're after. This is your reaction time, the amount of time it took for that ruler to reach that speed. So let's plug them in and rearrange. Let's plug in the 1.88. We don't need the minus 0 over t is equal to gravity 9.8. And you're thinking, where the hell's gravity come from? That is the acceleration there, if you're wondering. Let's rearrange it. So to rearrange this, we could put it in a triangle. Maths will tell you to do it the right way, so let's have a look. We would multiply both sides by t. T over t cancels out, so it gives me 1.8 is equal to 1.88 is equal to 9.8 times t. Then I would divide both sides by 9.8 and those cancel out, so that is our equation that we're going to use there. So let's try that. And again, if you remember, we said a reaction time is usually around 0.2, so 0.88 divided by 9.8, and in this case we'll get an answer of 192 seconds, which was a pretty good guess, wasn't it? Which is approximately 0.2 of a second. So you'll find for most people it ranges from about 0.17 to 0.22. We're all pretty much made the same. Now, what does that mean? Well, when you get a car, there will be a temptation to go really fast. Every year, without fail, I give this talk. Somebody ends up dinging a car. So let's take a typical scenario. You're in your car, and you're going 30 miles per hour. And you're in your car, you're going 60 miles per hour. So let's look at the typical change in distance. The first thing we'll do is let's put that in meters per second. So I get my trusty phone, and hopefully I can use Google. Here we go. Convert 30 miles per hour into meters per second.
30 miles per hour is equal to 13.411 meters per second.
Okay, and 60 miles per hour, funnily enough, will be 26.82 meters per second. So you see something in front of you. You're going 30 miles per hour like you should be in the area. So let's colour it in green for good. Let's have a look at how far you would travel in that time it took you to think. And if you remember, it's the time for it to go from your eye to your brain, for your brain to process it, send the signal to your foot, and you to hit the brake. So let's have a look how far you will have gone. The equation that links them is speed equals distance over time. Therefore, distance equals speed times time. 13.41 multiplied by my reaction time, 0.192. Get my trusty calculator out. 13.41 times 0.192. It means I would have gone, in the time it took me to think about it, 2.57 meters. So what about if I was going twice as fast? I will have gone 5.15 meters. I will have gone twice as far in the time. Now that doesn't take into account my stopping distance, my braking, because the braking distance, it gets worse, goes up even more. So let's take it. So here we've got, I'm going to shade that one in red for bad. So that's the first problem. You're going to have gone, no matter how hard you try, you will have gone twice as far in the time it takes you to think it. Next, and this one you're really not going to like. So this is advanced. This is kind of level 7, 8, 9. Your kinetic energy of the car is equal to the work done by the brakes. If your car's driving along, that's awful. Your car has a mass of 1,000 kilograms and it's moving along at 13.41. We can work out the kinetic energy, and to stop the car, the brakes are going to have to do work against the position of the car, right, to take the energy away. And the brakes will get hot and the heat will radiate away and your kinetic energy will go to zero, which is what you want. By the way, if you've lost the plot at this point, pause it, come back to it later because this is tricky. So let's find out. If my brakes could pull backwards with a force of 250 newtons, how far will I go? So let's have a go. First we start with kinetic energy. The equation, if you remember, is a half mv squared. So let's plug in the numbers. Half of 1,000 times 13.41 squared. So half of 1,000 is easy, 500. Back to my trusty calculator. 13.41 times 13.41 gives me 179.8. Times that number by 500, and we've got ourselves kinetic energy of 89,914 joules. So that's the first bit. That's how much energy your car's got while it's flying along. Let's shrink it, move it over here. Right, next. This energy that we've worked out, now the brakes must do work. So this must be equal to the work done by the brakes. Now if you remember, the equation for work done is force times distance. And this distance here is how far you will skid. Your skid mark. It will be huge. We know that the work done is 250. So all we've got to do is calculate 89,914 is equal to 250 times D. And I have a feeling my number is going to be ridiculously big. I think I've underestimated my brakes. But let's give it a go. Divided by 250 gives me, a stupid number, 359 meters. Now I wasn't aiming to get exactly the right kind of realistic number, but I want to prove a point here why people, particularly young people, crash. That's the distance you've gone, 3 2.59. You've got to add on to that your 2.57. Doesn't seem that important at the moment, does it? That would be your total distance travelled. Okay, going 30. Now, here's the kicker. This is the bit that catches everybody out. Imagine I was going twice as fast. So half of 1,000 times, not 13.41, but 26.82 squared. Now let's have a look at what happens to the amount of kinetic energy. It goes crazy. 26.82 times 26.82. Well, straight away that's 719 times 500. That gives me a total kinetic energy of, let me just tidy that up. Total kinetic energy of this time of 359,659.56. Now, you might not notice it, but from here to here, this number is 4 times bigger. When you double your speed, you get 4 times more kinetic energy. 4 times more KE. This is why people get it wrong when they start learning to drive. If you go twice as fast, you actually go 4 times further. So if we now plug our numbers into this, work done is equal to force times distance, and we do 359,656 divided by 250, we get a distance that's 4 times bigger. So divided by 250, 1,000, 1 kilometre, 438, let's call it 39 metres. Again, from there to there, you've gone 4 times further. So this is why people wrap their cars around lampposts before the age of 21 usually. So that's the key, that's the final point. If by now you're still awake, well done. If anything, walk away with this idea: thinking distance, braking distance together make stopping. That you can name a couple of the processes. If you're feeling fancy, what the ruler drop experiment is, so that's pretty easy. This is a tricky bit, is practice. Try it yourself, get someone to drop a ruler, catch it a few times, find the mean, try and work out your reaction time, and just follow the process. And the super duper fantastic difficult bit is proving that you go 4 times further with your stopping distance. That's a level kind of 8-9 question, but it's good practice. You've got to know your kinetic energy anyway. You know the work done equation, you're just putting the two together, so it's not completely impossible. Any questions, leave them in the comments. Take care, bye.